looks like we've got sort of critical mass of people showing up for this first inaugural MLOps community online meetup. So thank you all so much for coming. I really appreciate it. My name's Luke. I'm the founder and CEO of Dotscience, and we're kicking off this MLOps community in collaboration with our friends at BrizTech, which, as many of you may know, is a meetup group that's normally based in the southwest of England, around Bristol. But I think we probably have guests from all over the world today, because that's the wonder of an online event. I just wanted to quickly introduce my colleagues, whose nice faces you can see in front of you as well. So we have Chris, Dimitrios, and Mark here. So these guys are here to help get things started, and are available with if you have any questions on the chat. Please just shout. Oh, apparently you people can only see my face, but okay, that's fine. There are 3 other people on the call whose faces I can see. But yeah, great. So I wanted to start this event really by just sort of acknowledging that this is a strange time with the global pandemic happening, and that we probably most people are watching this from home. So I just wanted to acknowledge that it's a weird time, and that hopefully we can sort of come together as a community. And the way that we wanted to contribute was with this this MLOps community that we're kicking off today. The idea is to share ideas and best practices around DevOps for machine learning. It's intended to be an open and friendly space, so everyone is welcome. And really, everyone here, you are the initial community. So this is really your thing, as much or more than it is our thing. So please do get involved. I think after 40 minutes, when we finish the talk, we're going to open it up so that everyone can speak, and so that we can have an open Q&A and discussion. I hope everyone's okay with that. Bear in mind that the session is also being recorded, and we'll put it on YouTube later. So if you don't want to be recorded after the 40-minute mark, then just keep your camera off and your microphone muted. And feel free to use the chat. But yeah, so this is really our channel as a community. If you have ideas for talks or ways to use the weekly time slot that we have here, then please speak up, either at the end of this session after 40 minutes, or in the Slack or on the forum on MLOps.community. So yeah, please don't be a stranger. I also just wanted to acknowledge BrizTech. I already mentioned BrizTech, but a huge thanks to Nick and Thomas at BrizTech, who've helped us get the word out about this meetup, and they are sort of founding partners for this community effort. So I'm going to jump straight in. I'm going to share my screen and go through the first talk of the evening or morning, depending on where in the world you are. So hopefully everyone should be able to see my screen. I'm just going to assume that it's working, because Zoom does normally work. And I'll also pull up the chat so that I can see people's questions or comments as we go through. So the talk I wanted to present today is really an introduction to what is MLOps. Obviously, if you came to this meetup, you probably have some idea and you probably have an interest in it. But I wanted to sort of start these sessions with an introduction. And I also wanted to put a little spin on it, which is, how will MLOps properly done actually help me work from home? Because it's now becoming the new normal, that especially for well, it's becoming the new normal that everybody in the world is working from home, which is kind of crazy, kind of interesting. And in particular, if you're a data scientist or someone managing data scientists, then working from home and working remotely and doing asynchronous collaboration can be particularly challenging because of some of the complexities. So I'll also talk about that. And then I'm going to do a live demo. So please, could everyone pray to the demo gods? I'm going to attempt a live demo of some of our collaboration tooling. And then hopefully we have a good chunk of time afterwards for Q&A. So to jump straight in then, what is MLOps? MLOps is the intersection of these three disciplines, DevOps, software engineering, and machine learning. And so I'm going to talk for a short time about each of those disciplines in turn, and then I'm going to talk about how the intersection of them is kind of interesting and complicated. So if we look at how software engineering has been done, I'm not going to spend too long on this, but the basic point here is that software engineering has changed a lot in the time that it's been even a discipline. And we used to all log into big mainframes. We used to email patch files around to each other. And the way that, that collaboration happened for software engineers used to very much be around sort of manually integrating changes to source code. This was prior to version control, prior to things like Subversion. And for the longest time, the Linux kernel, for example, was developed by people just emailing patch files around and maintaining their own local copy of the source tree. And that was painful for obvious reasons. And it took a long time to integrate things. And then Subversion came along, and we got to the point where we had version control and you could check in and check out things, and that was a great improvement. And then the additional sort of improvement beyond that is this notion of distributed version control, where you can sort of do social coding on GitHub. And that's kind of, in my mind, from a collaboration perspective, where we've got to from a software engineering perspective. And so the next piece is DevOps. And so if software engineering is how we create software, then DevOps is how we deploy it and operate it. And DevOps has also undergone some significant changes in the last few decades and years. I am personally responsible for being one of the people who used to edit code live on the server. I don't do that anymore, but that used to be the way that a lot of things were done. People also used to build binaries and email them around. So people used to, for example, send WAR files, email a WAR file to a sysadmin and get them to deploy the latest version of the software on the server. And obviously that had problems. And then this thing happened that was called DevOps. And DevOps is about breaking down the silos between dev teams and operators. And so it was kind of a change in the way that teams are organized, and it's also a change in the way that the software is deployed and managed. So now the people who write the software are responsible for shipping the software and operating it in most well-formed DevOps teams. And continuous integration is a thing. So software gets continuously automatically tested whenever changes are pushed to version control. There's also been a big move away from running your own hardware towards the public cloud. And more recently, there's been a big move towards using immutable infrastructure like Docker and Kubernetes, and even this notion of GitOps, which is that you should also store the configuration for how your software is operated in version control, as well as the source code for it. And then source control becomes your source of truth for the software that, or the infrastructure that you're operating, and that has some obvious benefits. And then finally, the third discipline that's intersecting here is machine learning. And machine learning is basically how we use data and maths to train models to make predictions about the world. And I won't go through the whole history of machine learning here, but just to say that sort of there was this thing that's called the AI winter, which is where there was a lot of hype around AI kind of the first time around. I think it was in the 70s. People in the audience may well correct me on that. There was a lot of hype around AI, and it turned out that both the algorithms but also the hardware wasn't good enough. It was a little bit like the dot-com bubble in the sense that the internet speeds back in 2000 weren't good enough, and the hardware wasn't good enough the connectivity wasn't good enough to support all the hype that was going on about the web. And this AI winter led to this sort of huge peak in hypiness around machine learning and AI that then kind of collapsed when people realized that it wasn't actually going to be able to deliver on all the hype. And we've kind of gone around that cycle once already, and now we're in another hype cycle around AI and machine learning. And now this time around, it does seem like it is set to seriously change the world, really, and to change the way that, and it's starting to get adopted very seriously inside lots of large enterprises, which is interesting. And I also just wanted to have a nod here to the picture in this slide. Comes from a local Bristol company called GraphCore, and they make some very beautiful pictures that are representations of sort of visual representations of how neural networks actually work, which are pretty cool. And so basically, deep learning is now becoming, and machine learning and deep learning is becoming computationally feasible. And there's this huge rush that all the enterprises around the world are in. They're kind of locked in an arms race to get value out of AI. And so we end up in this place where machine learning is effectively emerging from research and it's being productionized, or it's like companies are attempting to productionize it. And this means that ML is emerging from research, and that these disciplines of software development, DevOps, and machine learning need to converge so that people can build models and they can deploy them, and they can have the same level of rigor and reliability that software has in DevOps. And so this convergence of these things will be called, and is already called, MLOps. And that's why we've named our community after this new emergent term. Now, so I personally believe that AI and machine learning has the potential to reinvent the global economy, and hopefully in a good way, because I think it has the potential to eliminate a great deal of boredom that is currently suffered by humans in doing very tedious jobs. It's kind of outside of the scope of this talk to talk about the political changes that are going to be necessary to make that non-disruptive. But anyway, so I think we can all agree that AI has the potential for good. And as a discipline, what we found is that it's extremely immature. So it's kind of like the Wild West out there. And we've seen damaging levels of chaos and pain as companies go from what we call playing with AI to actually trying to use AI to deliver business value, which is often referred to as operationalizing AI. And so some of the things that we've seen that cause these pain points are things like models being blocked before they can even get to deployment. So we've spoken with many companies that are trying to do AI in production. One of the things that is a very common theme is that we just can't. We can develop the models on our laptops, but we just can't get them deployed into production. And of course, that sucks, because then the time to value is very, very high. If it takes a long time, or if it's not even possible at all to deploy models, or even if it takes 3 or 6 months to deploy a model, then by the time you've got the model deployed, the data is already stale, and often AI projects in companies get branded as a failure just because they can't get them out the door. Another problem that we've seen is that models aren't monitored. That's actually item number 6 on this list. And so we had one company tell us that they deployed a model to production, and then the model went wrong, and they lost an unmeasurable amount of money, as in they actually couldn't figure out how much money they'd lost because the model had gone wrong, because they weren't monitoring it. And there are unique challenges around monitoring models that are different to monitoring regular software microservices that I'll talk about in a minute. Some other problems that we've seen are that people end up wasting a lot of time. So if there are multiple data scientists or machine learning engineers collaborating on trying to work on a model together, then a lot of time is wasted just trying to set your development environments up so that they are similar enough to that your work is, that the work that someone does is compatible with your environment, or spending a lot of time copying data sets around between different machines. This also kind of ties into the third point here, which is a lot of inefficient collaboration. So we've heard of people saying things like, oh, we just keep our data science team small and we keep them in the same room, so they can collaborate by talking. And obviously in the current climate, that is particularly challenging because you don't want to put people in the same room anymore. And even using paper notebooks to keep track of the work that they're doing and the results that they're keeping track of. And that relates to the fourth point, which is manual tracking. We've seen an awful lot of companies that they put the code, like some reference to the version of the code and the data and the parameters that they use when they're training a model, along with the whatever, like metrics, like accuracy score for that model. They either put that in a wiki or on paper or in a shared spreadsheet. We've seen an awful lot of shared spreadsheets kicking around. And there's another problem with those spreadsheets, is that there's a lack of reproducibility and provenance. And what this means is that you can't go back from a model that's running in production to, well, what data was it trained on? What parameters were used? Like, who even created this model? Do they even still work at this company? Like, being able to keep track of the work that went into creating a model causes lots of complexity when you're trying to scale up the team or when the number of models that you have increases. But the key point here is that if you can't deploy your models into production at all to begin with, then you're not going to get to the later problems of a lack of reproducibility and provenance. And so actually the most fundamental thing we need to solve in MLOps is making it easy to get models into production in the first place. And so this is kind of oddly familiar because we've been here before. And if you look at how software engineering was in the 90s, it was very siloed. Not everything was in version control. There was no continuous delivery. And it took a long time to ship software when it was being manually integrated and when there were these long QA and release cycles. And now software ships in minutes, sometimes in some cases seconds. Modern tech companies that are shipping software will often say when they onboard a new employee, well, on your first day, your job is to make a live change to the product, a small one, but you push it through the continuous delivery pipeline and get it out. We make dozens of changes every hour in some cases to different microservices. But AI is kind of still stuck in this pre-DevOps world of collaboration, and a large part of that is because the tooling isn't up to scratch. So we have this kind of manifesto. So this is what we care about, and why we get out of bed in the morning is because we're working on trying to solve this MLOps manifesto. And the manifesto is in the form of 4 tests. So you can kind of apply these tests to your own MLOps pipelines, and you can sort of form an opinion about how mature you are against the different requirements here. And so the first requirement is that your model training and deployment pipelines have to be reproducible. What that means, a good test for this is if I can come along 9 months later, if someone else can come along 9 months later and retrain a model that was trained by somebody else without even talking to them, with, let's say, an old version of TensorFlow on an old data set with on hardware that is sufficiently equivalent that they can retrain the model to within a few percentage points, then you've got a reproducible MLOps pipeline. And if 9 months later you can't because you upgraded the version of TensorFlow on your development machines and the data's gone somewhere and you don't know where the data's gone, the data's changed in your production database, then you've failed the reproducibility test. And if you fail the reproducibility test, then you're in trouble from a governance and compliance perspective in some industries. The second test is your MLOps pipeline accountable? And we talk about accountability from the same perspective that we hold humans accountable for their decision-making process. And one of the ways in which you do that is you say, on what basis did you make your decision? And the on what basis question with machine learning as a minimum requirement, not even going into the whole area of explainability, but as a minimum requirement, you have to be able to say what version of the data was the model trained on. And so you need to be able to track the model back to the provenance of where that model came from, what data it was trained on, by whom, and so on. The next point, and it's especially pertinent at the moment, is this collaboration requirement. So it has to be possible to do asynchronous collaboration. And this is something that software DevOps has got sorted, and MLOps doesn't yet, mostly. And this means that I need to be able to, for example, if my colleague Chris is working on a model, I need to be able to make a fork of that model, and I need to be able to make changes to it without treading on Chris's toes. So we both need to be able to collaborate asynchronously and get useful work done. Now, this has kind of influenced the design of what we're building to a large extent because we believe very much in the sort of GitHub pull request style of collaboration that the data scientists are familiar with. And there are some challenges in making that possible for ML. And then finally, the model development process has to be continuous. And so there are a couple of things that I mean by this. The first one is that the development process must be automatic. The deployment process, sorry, must be automatic. So it must be possible to automatically deploy a model into a staging environment or production environment without manually emailing Jupyter notebooks or TensorFlow files, sort of serialized TensorFlow models around, because as soon as you start doing things manually, then it introduces this possibility for human error. And the other piece is that you have to be able to statistically monitor your models. And this is interesting because monitoring models is quite different to monitoring regular software that you might deploy as microservices. And the reason for that is that when you monitor software, you can monitor things like latencies and error rates. But when you monitor when you monitor models, machine learning models, they can be giving you perfectly normal latencies and perfectly normal error rates. And the model can have gone completely haywire. And the reason for that is basically, if you already knew the right answer for what the model was predicting, then you wouldn't need the model. In other words, the production data is unlabeled. And so this means that it's challenging to understand the behavior of your model once it's running in production. So an example might be that I might have deployed a model for autonomous vehicles that classify road signs. And so you might have a bunch of cars driving around with models running on hardware in the cars and sensors, cameras basically, on the cars that are looking around for the road signs. And if you already knew what road sign the sensor was looking at, then you wouldn't need the model, right? But at the same time, it means that it's hard to understand the behavior of the model in production. And there are some solutions to this, including looking at the statistical distribution of the classifications the model is making, if it's a classifier. And then you can say, well, if the actual distribution of classifications drifts very significantly from my expected distribution, like the distribution that I used in training, in the training set, then maybe page a human, like fire an alert and get a human to look at what's going on, because either you deployed a bad model, in which case, you need to know about it so that you can roll back and so that you can figure out what went wrong with the new deployed model, or the world changed. And especially with things like computer vision, it's often surprising like how the models actually distinguish features in the data, and you can get stupid things like the computer vision model might never have classified any, or never be trained on any stop signs in the snow. And for some reason, it can't classify stop signs in the snow. So suddenly it snows over a large part of the country, and then your stop sign classifier stops working. And obviously you're in trouble, so you need to have that statistical monitoring. So those are the requirements, and so I'm going to talk about how we can try and address those requirements using MLOps tools. And just before I do that, I want to talk a little bit about how the software lifecycle, sorry, the MLOps lifecycle is just fundamentally more complicated than the software development lifecycle. So when you're doing software development, and life is easy, kind of. It's easier anyway, because all you need to do is you need to think about versioning specific versions of your code. Because as long as you're Dockerizing things, then you ought to only need to know exactly which version of the code was used, plus the Docker file and the dependencies, in order to reproducibly build the same, or effectively the same, deployable artifact. And so you can create code, you can test that code in CI, you can deploy that code into production, and then your monitoring system can tell you how well it's performing. Maybe you need to upgrade a database, maybe you need to go and optimize a certain code path, and you can go around this loop as quickly as you can. And that's basically what we're doing with DevOps. But with machine learning and MLOps, you've got this fundamentally more complicated thing going on, which is that you've got data coming into the system, which is a major form of entropy, and you've got code that's being written to train the models, and you've got parameters which are being fed in to training the models. The model runs, the model training runs, sorry, and all of these things combine. And before you even train a model, you've also got the data runs, which is when you're doing feature engineering, or you're filtering or splitting the data. And so you're executing a certain version of a piece of code against a certain input data set and creating an intermediate data set. That's what a data run is. Or you're running a certain version of a piece of code against an input data set, like a test, training, and validation set. And then you're creating a model as an output. And so when you're doing ML, when you're developing machine learning models, you are doing these data runs and these model runs, whether you're keeping track of them or not. These might be the cells that you run in your Jupyter notebook, or the Python scripts that you run on your laptop. And these runs are happening. You just haven't given a name to them. And so what we've realized is that it's really important to introduce this notion of run as a kind of a building block. It's a fundamental object in the system when you're doing MLOps. It's this version of this piece of code ran in this environment with this input data and these parameters, and it created this output. And one of those types of outputs, like I said, is models. And then the model itself, the serialized model file, is the deployable artifact. It has some metrics associated with it, like how well it performed against the validation set. And then it's that model that you're deploying into production. And then you're monitoring in the way that I described, that monitoring models is different to monitoring microservices. And then your monitoring might actually cause you to go back around all sorts of different loops through this diagram. So that's kind of the flow that we're looking at here. So I'm a little short on time, so I'm going to skip over the life cycle quickly. The life cycle is really just a visual representation of how the the diagram I just showed you is cyclic. And so you do data engineering, you need to keep track of the data runs when you're doing things like feature engineering. And then you train a model, which means you take a certain version of the data and you train the model, and out of the model development process come serialized models, typically Docker images with serialized models baked into them. And then those serialized models get run in production or staging and then production. And then there are these kind of two feedback loops. There's the statistical monitoring feedback loop, which is the fast one, where you can say, show me the behavior of my model in production in real time based on like the distribution of classifications it's making. And then there's also this slower feedback loop, which is that you retrain the models with new data as you get new data coming in. And of course, the model making decisions can change the world, and so can also impact on the data that is being recorded in the database. So that's kind of the MLOps lifecycle, and hopefully I've adequately answered the first part of the talk title now, which is what is MLOps? My opinion is that MLOps is not just about operating models, it's actually about the entire lifecycle of doing data engineering, training models, and then getting models into production. And it's about being able to implement this process in your company or in your organization with the same level of rigor that sort of best-in-class DevOps and software engineering teams manage. And so let's kind of take a step back then and say, well, how can properly implemented MLOps help me in the current global situation that we have, where we're now all suddenly working from home? And in brackets, if I'm a data scientist or a manager of data scientists. Well, the answer to that question comes down to the collaboration piece that I mentioned earlier. So let's kind of do a deep dive on collaboration. So there are two fundamental modes of collaborating between different people doing work. There's synchronous and there's asynchronous. And synchronous collaboration is when people are sitting in a room together and they're interrupting each other when they have a question and when they need to get something done. And in particular with machine learning, it might even be that they're sharing an environment. So they might even be pair programming, sharing a text editor. So they take it in turns to use the keyboard. They would be working on exactly the same data set in exactly the same environment. And then you're kind of time slicing it. Well, hopefully pair programming is effective, and okay, so people can't make changes to this thing at the same time, but we just kind of take it in turns. Or there's an asynchronous approach, which is to say that different people should be able to work on different copies of things. And the problem with an asynchronous approach, of course, is that you then need to be able to cope with conflicts, like merge conflicts in Git. Which takes me on to the second point here, which is how do software and DevOps teams do it? Well, with GitHub, basically, and tools that are like GitHub, like GitLab and Bitbucket and all of the tooling around that. And the way that works, as I'm sure most of the people in the audience know here, is that you can fork someone else's project effectively, or or you can make a branch from master. You can make some changes in your branch, and while you're making the changes in your branch, you're not treading on anyone else's toes. And when you then propose those changes back to the master branch, that's when you can pull in new changes from the master branch and integrate them into your branch. And that's when you have to deal with merge conflicts. And then you can propose a version of the change which is up to date with respect to the master branch. That's basically commonly known as Git flow. And it's been very successfully used in pretty much every team on the planet. People have tweaks to that approach with multiple master branches and so on, but it's all fundamentally the same idea of asynchronous collaboration. And then with DevOps teams adopting things like GitOps, where your source of truth for what's running in production is also in a Git repo, well, you can use tools like Terraform, or you can version control your Kubernetes YAMLs, and then happy days. You can use the same collaboration approach of pull requests when you're deciding to scale up the cluster or deploy a new database and doing the other things that DevOps teams do. So what are the challenges applying asynchronous collaboration to machine learning? Well, they are numerous. The first problem is that Jupyter notebooks don't version control very well, and a lot of data scientists use Jupyter notebooks. Another challenge is that data versioning and data sharing is difficult in a machine learning context. Sorry, in a collaboration context, because you can't very easily put your data in Git. There is a project called Git LFS, but it has some significant restrictions. And so what we find is that teams normally just don't bother with data versioning, and they just rename files or rename folders and have folder names with like _final and _final v2 and all these funny little strings that refer to the things that have been done, and then they have to share those folders around, and it becomes quite messy. The other thing is metric and parameter tracking. You didn't have to do that when you're doing software, but you do have to do it with machine learning. You have to keep track of which parameters you used and which accuracy score you got, because models aren't either sort of green or red. They're not either working or broken. They're kind of somewhere in the middle, and the metrics, like the accuracy score, will tell you how good a model is against a certain test set. And so you need to keep track of that, and you could put that in the Git commit message, but then you have to have a human remembering to do it, and people are bad at remembering to do things. Or you can use tools that help you with experiment tracking. And there are challenges with using a combination of local development environments. So you might have a GPU or an IPU in the machine at your desk, or you might be using machines in the cloud. And with Git, it's quite easy to switch from a local machine to a machine in the cloud or a machine in your data center. But doing it effectively with machine learning, where you've also got data that you need to move around, and you've got to keep track of metrics and parameters, and maybe you can't even really use Git with your Jupyter notebooks and still do effective collaboration. It makes it all a lot more challenging with respect to kind of moving around where you're doing the work. And so there are some tools that help to solve these problems for machine learning, and it's actually a very exciting space, and there's lots of new innovation happening around this. And so obviously, I'm from Dotscience. I'd love it if you started using Dotscience, but I also wanted to give an acknowledgement to the fact that there are lots of other tools out there. And so MLflow is quite strong in the experiment tracking space. Weights and biases is very strong in like comparing the relationships between metrics and hyperparameters. DVC is a promising project in terms of doing data version control, as is a project called Pachyderm. And then in terms of diffing and merging Jupyter notebooks, there's an open source project called NBDime. In fact, many of these projects are open source. And so what we've tried to do with Dotscience is bring the capabilities from these kinds of capabilities into a single tool. And so I'm going to attempt in the next 5 to 10 minutes a very quick live demo of the collaboration tool that we've developed that allows you to collaborate on Jupyter notebooks and do data versioning and sharing, keep track of metrics and hyperparameters, and to move around where you're doing your work and automatically synchronize the data and so on for you. So what I started doing earlier was kicking off these runs, and so let's see, we have a couple of different projects here, and we've got a couple of different users as well. So what we've got here on the left-hand side is this user called Luke. That's me. And then I have a collaborator over here with the yellow browser, whose name is Fred. And Luke and Fred have been doing some work on a project. And so you can see that in Dotscience you can see the work that they've been doing, and you can compare the runs that they've been doing on this project. And so you can see that sort of in the mists of time 5 days ago, Luke did this run which used one epoch and the SGD optimizer and got an accuracy score of 58%. And then Fred did this pretty awesome run that got 92% accuracy. And then Luke tried another combination of parameters and got an accuracy score of 84%. In this view, this is kind of Fred's view of the world. So Fred is operating on a fork of Luke's project. So let's go and look at the history of the runs in the project. So we can see here, well, back in the mists of time, somebody converted a sign names file from CSV to JSON. So it looks like this is a road signs project. So this classifier is going to be used to classify road signs. And so what we've built here shows the ability to keep track of the provenance of data. So this is an example of a data run. So we have this certain version of this code read in this certain version of this input data, and it wrote out a certain version of an intermediate data set, the classes.json file from signnames.csv. You can see who did it. You can see which Docker image was used. So that kind of pins down the environment. And you can also go in and look at the files. And so you can see it was exactly this Jupyter notebook was used to convert these sign names from CSVs to JSON. And so what we've introduced is this notion of the Dotscience Python library. And in the Dotscience Python library, you can read in, you can do things like ds.start, which says this is a new run. I'm going to do something here that is constitutes a separate run, execute some code that reads some input and creates some output, basically. And then I'm going to mark certain files as input files and other files as output files. And then I'm going to do ds.publish. And every time you run ds.publish, what we do is we take a lightweight file system snapshot. And that lightweight file system snapshot contains metadata about, contains both the actual data that was used, so it versions the data set that's there on your file system in your workspace. And it also records the relationship between certain input files and output files. And so we can see, okay, we converted sign names. Looks like we also downloaded some data. So we downloaded some data from the internet here. We then trained this TensorFlow model. And then the TensorFlow model has the most interesting provenance graph that we've seen so far, which is that it reads in a certain version of a data set and it writes out a model. And this model, the serialized model, is the thing that can then be deployed into production. And so from in here, we can deploy a model into production. And we've already got a few running. We've got, no, we don't have any of these models running actually, but we have models that are built and ready to go. So from that, those files on disk, we can then build a model into a Docker image and deploy it to a Kubernetes cluster. But I'm not going to show you the deployment and the monitoring stuff. We can probably talk about deployment and monitoring in a later meetup if people are interested. And instead, we wanted to talk about collaboration. So I tried something earlier, which was that, so we've already had a pull request in this project previously, which was that Fred said, hey, you should get better accuracy if you try these parameters. And so you can see that the diff of exactly both the model files that changed when that pull request was made, but also the parameters that were changed. Then you can also, so let's see. It looks like Luke and Fred have made conflicting changes to this model, because since sort of the last common snapshot here, the last common run, they both made new runs which change the same thing. So there's the most recent run here uses the Ada Max optimizer and got 84%. And this one went back to using the SGD optimizer for one epoch for whatever reason. So if we go here, this is just like the Git approach, which is that or the GitHub approach, which is if you want to make a pull request, you first have to get your local branch up to date with respect to master. And in this case, we're going to think of Luke's version as master. So before Fred is able to upstream these changes, he's going to have to go ahead and update the project from master, because the fork is 2 commits ahead and 2 commits behind. Let's see, I just need to click this button to update from origin. It's going to copy a bunch of files into my fork, and so it's kind of copying Luke's latest version, and then at that point it will be able to show me the diff from one version to the next of exactly what's changed. And it will also be able to provide a sort of 3-way merge algorithm that allows me to say, oh, I want to take this change but not that change, and so on. That's what we're working on. It seems like this is going to spin forever, so obviously we didn't pray to the demo gods hard enough, but you can kind of get the idea of the things that we're doing, and hopefully this was useful. So I'm going to open the floor up now to questions, and I think if we experiment with the Zoom UI here, we should be able to invite everyone into the conversation to ask questions with their voice if they want to. And I see that we've also got some questions in the chat. So I'm going to stop sharing my screen. And
yeah, super. Look, this is Mark here, and Waleed had a couple questions in the chat, both about MLOps and then also a question about Dotscience, if you want to take a look at those.
And I think, Luke, the way it's set, you have control to unmute everyone.
Cool. So I think I can't do that all in one go, but I can promote everybody to a panelist. So I'm going to try and invite everyone to be a panelist, and then if you want to kind of come into the room, as it were, and ask questions, then feel free. And then hopefully in the next 10 minutes, I don't know about everyone else, I can go a few minutes over, then people are welcome to unmute. But yeah, Chris and Mark, can you see the more button next to the attendees that then it says promote to panelist?
I don't have that view.
Oh, okay. I'm just going to go through and click that button for everybody.
Well, Luke, well, maybe as you do that, Waleed, looks like you've been kind of promoted, as it were. If you want to put your questions, pull them out of chat and put them into the real world, and I think Luke can speak to them that way. You'll have to unmute too if you're there. There you go.
I see some awesome backgrounds.
Luke, you want to make start with Waleed's message there in the chat? I think the question is, how about ML operations, provisioning infrastructure, platform frameworks in a consistent, repeatable way? Where does that fit in ML ops?
Yes, I'm nearly done clicking the promote to panelists. And as you know, Mark, I'm bad at multitasking, so I'm not even going to try. Okay, cool. So everyone's a panelist now, so welcome to the room. Waleed says he's not sure if the mic is working. So I'm just going to go through these questions in the chat, but feel free, folks, to unmute and get involved here. So how about ML operations, provisioning infrastructure, platform frameworks in a consistent, repeatable way? Where does that fit into MLOps? I think that's definitely part of the job of an MLOps platform, is to enable the provisioning of infrastructure. So one of the things that we've done, for example, is we've made a Terraform repo that you can use to spin up a Dotscience deployment, and then from that Dotscience deployment, it then hooks into the underlying cloud provider to allow data scientists to self-serve compute from the underlying cloud provider, so they can provision a machine with a GPU if they need to for a short period of time while they do some training, and then they can switch it back to a CPU. And we've also made it so that those machines shut themselves down quickly within a couple of hours of becoming idle to save on costs. And then a related point is that it's kind of a multi-cloud point, is that it needs to be possible to attach compute from multiple clouds and also from on-prem. And so I definitely see it as part of the responsibility of an MLOps platform to include that component. Basically, the necessary sort of storage and network virtualization that you need to be able to attach compute in a flexible way from all over the place, from a machine sitting under your desk or a machine in the cloud. I hope that answered your question, Waleed. There's also a comment here: if I understand correctly, Dotscience is a multi-tenant, multi-project with teams in mind and has some sort of end-to-end data science in mind. Yes, that's correct. Eduardo, is your mic working? Do you want to ask your question on voice?
Hey, hello.
Hey, how's it going?
Hey.
I can hear you.
Yeah, let me try to see. Can you see me now?
Yes, greetings. Hi.
Hey, I'm kind of light, so I have a question. In fact, I shared in the chat, but I can repeat. So I found it very interesting you use the word or the term collaboration tool.
Mm-hmm.
Why you choose that term? Because are you, as I understand, you are trying to achieve, or at least to define, and when I think collaboration, I think communication.
Mm.
So you're thinking like a communication flow?
Yeah, definitely. And I think that comes down to what we're basically trying to do is mimic GitHub, but make it work for machine learning. And that means you have to keep track of data, and you need to keep track of models, and you need to keep track of metrics, as well as keeping track of versions of code. And it's by packaging them together as runs is what enables that to happen. But in terms of the communication, yes, it's about not having to jump on a Slack call or a Zoom call and interrupt someone if you want to collaborate with them. Instead, it should be possible to do things asynchronously in the same way that that software engineers are familiar with, as doing pull requests and working on branches, and then you can have your pull request reviewed asynchronously by someone who's awake when you're asleep if you're working in different time zones. Mm-hmm. Cool. Yeah, any other questions or comments from the group here? Oh, we might finish on time then. Cool. Yeah, I just wanted to wrap up then and say thank you so much for coming. I think we're planning on running these every week. I think we have our next speaker for next Wednesday confirmed already. He is a guy called Charles Radcliffe, who is formerly the head of AI for Fidelity International. So he'll bring sort of an enterprise perspective. Fidelity, as I'm sure you're aware, is a pretty big organization in the financial world, and Fidelity International in London is where he's hailing from. And he's going to talk about best-in-class AI governance in financial services. And yeah, if folks have other suggestions for talks, please shout out in the Slack channel or post a message on the forum. And yeah, thank you all very much for coming to the first ever MLOps community meetup.
Thanks so much, Luke. Appreciate it. Thanks again to everybody out there for joining the conversation, and hope to see you next week. Awesome. And yeah, we're going to follow up, by the way, with an email with a link to the presentation in it. Yeah, if you're not already on our Slack channel, please come and hang out on Slack. Awesome. Thank you, everyone.